Hello everyone and welcome back. We are back to school and we are starting calculus, and so we're going to kick off today with our first lesson, which is limits. And we're going to start doing that in a visual sort of way. So to kick off, I would like to start here. We're going to take a look at a table. We're just going to build a concept here. And so the first thing is take a look at the table and what number do you think goes in that blank? Now remember, as you watch these videos, at times you're going to want to pause. I'm just going to run through all the stuff. If you want to pause to take notes or to try this stuff on your own and see how close you can get to the actual video, I would really encourage that because I think it's going to help you learn. So anyway, here we go. Taking a look, what number belongs? Well, it looks like maybe 5 is what a lot of people say, but why couldn't it be 12? I mean, couldn't that just as easily be 12 or 1200 or 12,007? I mean, there's no reason why it couldn't be. We don't know that, but what we're trying to get at with a limit is that we're trying to say, what does the pattern indicate is most likely going to happen? And so we want to look one side at a time. So if I look just at these top numbers, I mean, yeah, it seems like 5 would be a reasonable fit to the pattern to go there. If I look at the bottom set of the numbers, looking at our y values or our function values, yeah, it looks like it would be reasonable for a 5 to be there. And so when we look at a limit, we say the limit as x approaches 2 of f of x. We're not saying that the number here is actually 5. But what we're saying is that based on the pattern, it appears that on either side of our x value, less than and greater than, it appears that the y values or function values are converging together at 5. And again, it does not mean that f of 2 is going to be 5. We don't know that. We're not claiming that. It could be 500 again. I mean, we just don't know. But that's the claim that we're making. Okay, we're going to do 3 of these so we can try to get the hang of it a little bit before we get into some actual limits. Let's go down to the next one. We look at this one. Here's another table. And ask yourself the question, what number belongs in that blank? Well, it's interesting. I've taught this twice in the last 2 days, and one class was absolutely certain it was 4, and the other one said, I don't know, who knows? Well, it seems that our brain wants to try to fill in blanks and fill in gaps, because, I mean, sure, it could be 4, but if you look at the patterns present in the table, there's not necessarily much that suggests it should be. So, for example, look only at the numbers, the x values, that are less than 2, because we are approaching 2. 3, 3, 3, look at the pattern, it suggests that perhaps maybe the next number should be 3. But if we look just at the bottom half of the table, then the suggestion is maybe 5, 5, 5. Well, maybe that number should be 5. Well, let me tell you, when we're dealing with limits, we can only have one. So do we average them? Or maybe it's 35? Or no, if we can't agree, if the patterns don't agree, then it's nothing at all. And what we say in that case, yes, from the movie Mean Girls, we say it does not exist. The limit as x approaches 2 of f of x does not exist. Okay, let's look at our third example. In this third example, we're going to look at the pattern again. We're going to try to find the missing number, and this is the one that there was a little bit of confusion about today. So 5, 10, 15, well sure, the next number is 20, right? And then it starts over 5, 10, 15. But if you only looked at the numbers that have x values that are greater than 2, 15, 10, 5, maybe you'd be convinced that instead of 20, 0 is a more logical approach to this. Well again, if there are 2 different numbers, the limit does not exist. So that's what we're going to say. There is not an obvious number that belongs there because of the pattern on both sides. And so instead of writing it all out, we can go ahead and just write D and E. Does not exist. We can use the shorthand for it, and that is just fine. So for calculus, there's a couple things that we really prefer. For now, we would really like it if we were dealing with functions. That would make things a lot easier. So our short functional definition, functional definition for this, is that it's going to be some sort of a relation relating 2 sets of numbers in which every one input creates exactly one output. And when we do that visually, we need things that pass the vertical line test. So for example, if I take a circle and I put a vertical line through it, right here we have our input, that's our x value, we'll call it x sub 1. It is relating to 2 different outputs. I'll call them y sub 1 and y sub 2. So it's not a function. The vertical line hits it twice. However, if we have something like a little parabola, any vertical line can only touch the parabola one time, and that suggests that it's a function. Okay, so we like things to be a function. The other thing we really like for our functions to be continuous for calculus. That makes it a little bit easier. And there's a couple different ways to understand continuity. The easiest one, that's maybe most palatable to a lot of people, is if you have some sort of a function or some sort of a curve that you're able to draw it without lifting up your pencil. So for example, we could have a cubic. Looks like this. I didn't have to lift up at all. We could have something like an absolute value graph. And even though it's got what we're going to learn later is called a cusp right there, I didn't have to lift my finger to draw that. But if I take something that looks like some sort of a piecewise function, I had to physically... Sorry about the disruption in the video there. Batteries, beginning of the school year, you know how it goes. But we're back, so let's do this. We were talking about whether or not these functions are continuous. I have another example for you. Another one would be like the function 1 over x, or any rational function really for that matter, where you've got something like this. So you draw down here, you have to physically lift up to continue the function. So asymptotes create a discontinuity. We'll talk about some other kinds of discontinuities a little bit later in the video. But for now, let's get into a little bit stronger definition. Now, there is a really hardcore definition that's like a 300 or 400 level college definition of continuity. We're going to skip that for right now, and we're just going to stick with the if I can draw it without lifting my pen or my finger, or this is kind of a shortened version, and these two together capture most of the essence of what continuity is. So for this, essentially, if a function is continuous at any point, then as we zoom in, there's always going to be an x value such that the y value, f of x, exists no matter how much we're doing the zooming in. And then we got a couple examples over here. We've got one here that looks like some sort of a cubic, it's continuous, and then here we've got something that looks piecewise, and as you can see we've got a discontinuity. In fact, on this one, we have no y value at all for x naught, which sometimes that'll happen, although the other thing that can occur is we could have one of these points filled in. So we could have a closed at that, and we could have an open right there, or we could also have a point up here somewhere. That can happen as well, and we're actually going to see an example of that here in just a minute. So let's get into a little bit more of the visuals of what we've been doing. And remember, we want to intentionally relate this to the tables that we were talking about. We looked at the patterns in the tables, we were looking at the numbers that were less than and greater than, using each of those patterns to see if the prediction would do the same thing. And so that's the mindset that we're going to have as we look here at this. So let me get these boxes out of the way. And so here we are. And we want to try to figure out what our limits are going to be. Oh, here's Mr. Fouts. And so we're going to start over here, and we're going to look specifically where we have discontinuities. So we've got one right here at x equals 0. And so we're going to look at this sort of pattern on either side. So as I trace the function to the left of that value, it appears that we're headed toward 0. And as we trace from the right, it appears that we're headed toward 2. Well, think about what that meant in the context of these tables. So back here, we said we look from the right, and when we look from the right, it looked like the pattern was suggesting that we would need a 5. Look from the left, the pattern was suggesting we would need a 3. They didn't match, so what do we say? The limit does not exist. And that's going to be the same thing on this visual. Another way to think about it, if you take your fingers and you trace the function on either side, do your fingers come together or not? I'm tracing, 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 and no, my hands aren't coming together. So at this point, that point being x equals 0, the limit does not exist. Let's find our next discontinuity and see if we can make heads or tails of it. Looks like that happens over here at x equals 2. And here I'm going to do the same thing. I'm going to trace from the left. It looks like we're heading toward negative 2. And I'm going to trace from the right, and it looks like we're heading toward 2. And it doesn't matter if we actually get there, because a limit is like a hypothetical question. If we're going to get there, where will we be in terms of our y value? So I'm tracing down, y value is headed toward 0. Tracing down, y value is headed toward negative 2. They're not equal, so the limit does not exist. And we've got one more. Let's come up over here to an x value of 4. And on this one, notice there's only one point missing on the graph. And so as I'm tracing from the left, it looks like we're headed toward a y value of 4. As I trace this way, it looks like we're headed toward a y value of 4. Or, if I squeeze in tracing the function, look at that, my fingers come together. And this is what people have the hardest time with, typically in my experience at least, with limits, is they say, but wait a minute! There's no point there, so how can that be the limit? Remember, it's like with the tables. We don't know that this number is 5. It could just as easily be 500, but the point is, if you look on either side, the pattern in the y values is telling us that we would expect that 5 would be the number there, and that's the essence of what a limit is. Okay? So let's look at one more. So on this one, we're also going to just focus on the discontinuities. If we're looking at places where it's continuous, like through here, it's a little bit easier. Discontinuities causes us to think a little bit more. So let's start down here with this one, and let's start talking about the notation for how we'd write that out. On this one, I'm going to see that my x value right here is a negative 2. So what I would write is the limit as x approaches negative 2 of the function f of x, and then we'll figure out what it is. And this gets a little tricky because notice this point right here. A lot of people get tricked by that point. It's kind of a trick question, in fact. So as we trace down this way, the y values are decreasing, getting lower, 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 and it looks like we're headed down toward negative 4. As I trace from the right side, tracing the function, looks like we head down toward negative 4. Or if you prefer, tracing with both fingers, tracing, 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 and they come together. That y value is what our limit is. So that's negative 4. But let's ask another question. What about the actual y value? Like if I ask for f of negative 2. Not a limit, just the function value when x is negative 2. Well look, there's nothing there. And so we have to figure out, someone said if we put a vertical line at that x value, where do we actually hit the function? And that occurs right up here. There it is. So that's our actual y value. It's not our limit, that's the actual y value, and so that is 3. Moving on to our next discontinuity, we're going to go over here, and so for this one I'm going to say the limit as x approaches 1 of f of x, and again we're going to trace from either side, tracing, 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 the fingers aren't coming together, or if you look just at the right side, the y values are decreasing, looks like they're headed toward a y value of 0, tracing on the right as we get really, really close to an x value of 1, looks like the y values are getting really, really close to 2. We know 0 and 2 aren't the same, so this limit does not exist. But what about the actual y value? Do you see it? Do you see where we actually hit a vertical line on the function right there? I hope not, because both of those are open circles, and there's no dot. Here we had a dot out floating in free space. There is no dot here, so this actually doesn't exist either, and we're going to denote that here with the empty set. One more. Let's go up to here. Looks like our x value is 4, so limit as x approaches 4 of f of x equals, well, let's see. Maybe you want to pause the video and try this one on yourself. Ask yourself, if we look at the pattern on the right and the pattern on the left, are they heading toward the same place? Are they going to meet up? In this case, it doesn't look like it. And the fact that this dot is empty and that one is full has absolutely nothing to do with it. It might trick you. It might try to confuse you. But it's totally unrelated. The y values here get really, really close to 4. This one is heading towards 6, not the same number, so the limit does not exist. Okay? We've got a little bit of a theorem we're going to throw in here, and this will make some of our calculations a little bit easier. And so what we've got is if we have a function that's continuous, and I've chosen a continuous linear function down here, if it's continuous at a point, then the limit at that point is equal to the function value at that point. And you'll notice here I've chosen a limit. This equation right here, this expression rather, is the equation that's represented here on the graph. So they are the same linear function, and we said at a point, that point looks like it's 0. And so it's saying the limit, whatever this answer is going to be equal to the function value at that point. There's a couple ways we can do it. We can do it visually, or we can actually do a direct substitution here. So looking at our graph, I'm going to find my x value of 0. There it is, trace down to the function, and boom, there you have it, negative 3. So that tells me right off the bat, f of 0 is negative 3. And since this tells me the limit is equal to the function value, limit is equal to the function value, without doing any extra work, that's negative 3. If you want, you can plug in a 0 there and verify it, but it will come out as negative 3 when you do that. Alright, these are the types of questions that we would normally see on a test. This is the first visual we looked at, but now we're seeing it in typed up notation the way it might appear on a test for you. And so I'm going to take a minute and fill these in. I would encourage you to pause the video and try these yourself first, and then you can check your answers with me. On this first one, the two sides are not coming together, so this limit does not exist. Function value, I'm looking for the filled in dot, so that's 2. At the second spot where x is 2, these two sides, they are not converging on the same y value, and so I have to say this limit does not exist. Looking for the function value, I'm looking for the dot that's filled in, that's a negative 2. In this last location, we've got a hole in our function, a point discontinuity, a deleted point, call it what you want. But coming into there, it looks like from the left and from the right, these two sides are coming together, and that tells me the limit does exist, and it's the y value of 4 right there. However, because that's open, there isn't actually a y value there, so I'm going to say that's an empty set. Okay? That'll do it for this first visual lesson. See you next time.